So what I want to talk to you today is work done with Rafael Wagner. He's the main responsible for this project. It was his master's thesis project, and he was a student in my group, a master's student in my group, and now he's working with Ernesto and Rui in Braga, and also with Alison Tezin, who is a PhD student at our group, and also Roberto Baldijão, who is a PhD student at Unicamp. And so I'll start talking about what we call resource theories. So this is just a powerful framework, mathematical framework for treating a physical property as an operational resource. And it is good for characterization of this resource and quantification and manipulation and many other aspects of this physical property treated as a resource. And these resource theories, they consist of mainly three aspects. First, we define what are the objects of our theories and which are the entities that may possess that resource. And the free objects, they are the entities that have no resource. We also need to talk about free operations, which are transformations of these objects that preserve the set of free objects. These are operations that do not create the resource from an object that has no resource. And also we would like to talk about quantifiers, which would give a quantitative notion of how much of that resource a given object has. And of course, we want this not to be only an abstract framework for treating this resource, but also we want relations of all of these aspects of the theory with practical applications. And this is the point that I'm going to treat in this talk. And the main results are in this work here that is available on arXiv. Okay, so since we have seen since the beginning of the week, there are many definitions or many different ways in which we treat non-classicality and different things that we call contextuality. So I will just give a brief reminder of what is contextuality in prepare and measure experiments, which we just call Specking's contextuality sometimes. So this is all based on the work of Speckens and works that followed it. So our main objects in this scenario are preparations that we will call PI, and measurements with given set of outcomes. And we will treat this in an abstract way, so I'm not interested in actual physical implementations of these things. I'm just interested in the statistics. So I want to use as an object here the probabilities of getting an outcome K, given that a preparation, that I'm making a measurement J in a preparation I. So these will be the main object for us here. So we can think of this as a scenario like this. So I have a box that prepares a physical system in different states. So I'll use these buttons here to choose which preparation this box will output. And then I have this measurement box here that in which I can choose which is the measurement that I'm going to perform. And it's going to give me some outcomes that also depend on the preparation of what is reaching this measurement box coming from the preparation box. And I'm always interested in the statistics of these things, not exactly what is inside these boxes. Okay, so now we define some notion of equivalence. So I say that two preparations are equivalent if they give the same probabilities for every measurement outcome that we have in our scenario. And we also define measurement event equivalences as measurement events that give the same probabilities for every preparation. So with these notions of equivalence, now we can talk about classical models for these scenarios. So I'll think of these classical models, we can think of it as a set of hidden variables. And for each preparation, I have a probability measure over the set of hidden variables. And for each measurement, I have a set of response functions in a way that I recover the probabilities of my experiment in this way, summing over all hidden variables and using this product to compute where are the outcomes for each possible value of the hidden variable. And of course, if I allow this to be anything, we can reproduce basically any probability distribution that I have, but I want to impose some restrictions on these models, and the restrictions that I'm going to impose here are that these functions, that these probability distributions and these response functions, they have to respect the operational equivalences. So if I have two preparations that are equivalent, the corresponding measures need have to be equal, and if we have two measurement events that are equivalent, the response functions have to be the same as well. So if models, if a set of probability distributions can be explained with such a model, satisfying these restrictions, I'll say that it is classical or non-contextual. Otherwise, I'll say that it's non-classical or contextual. Okay, so some examples that will be important later. So the simplest scenario has 4 preparation procedures and 2 binary outcome measurement procedures. And we don't have any measurement equivalences, but we have these equivalences for preparation procedures, or the 4 preparations procedures. We can generalize this simplest scenario. So this is the simplest scenario because it's the simplest scenario of this type where we can witness quantum contextuality in this sense that I just defined. And we can generalize this scenario in 2 ways. The first one is just considering a set of, an arbitrary set of preparation procedures. I'll imagine that I have an even number here. You will understand in a minute. And we have a set of binary outcome measurement procedures. And I, again, will not consider any measurement equivalences, but I'll consider this set of preparation equivalences. And we also have another generalization that I'll call BN, because this will be important in later, especially for the scenario B6. It will be important later. So I have a set of preparation procedures and binary outcome measurements, and I will consider these preparation equivalences, and I can consider other preparation equivalences, but that do not include the first 4, okay? So we have many possible scenarios like that. Okay, so now we will get these 2 things together. So now I will talk about research theory for this physical property, which is contextuality in these prepare and measure experiments. And the objects are just what I call behaviors, these sets of probability distributions that describe my experiment. And the free objects are the classical behaviors. And we defined a set of free operations here. I will not get into too much detail here, but we have an explicit parameterization for this set of operations. Here there is a tilde missing on this side, but we can understand this set of operations using this figure. So basically I'm just getting my original scenario, which is here in the middle, and I'm applying classical pre-processing here, pre-processing here, and post-processing here. So in this way, I define a class of operations that preserve the set of non-contextual or classical behaviors. So this set of classical behaviors can be characterized in terms of linear programming, as we discussed yesterday. And several quantifiers that have been discussed during this week and other notions for other definitions of contextuality can be generalized for this notion as well. And what we want in our work is the following. We want to use the resource theory framework that I just presented to you briefly as a tool to analyze the structure of prepare and measure scenarios and the classical and quantum sets of behaviors in these scenarios. So this goes much in the direction of what we discussed yesterday about why would I need to devise sufficient conditions if I have a way of characterizing these sets using linear programming, for example, for the classical set. So what we get with this is that we simplify proofs for quantum contextuality, and also we have some other aspects in arguments regarding robustness for experimental implementations. And we can witness quantum contextuality with associated to non-trivial inequalities for a class of interesting scenarios using a connection with measurement simulability, and we have a connection with practical applications of this notion of contextuality. So briefly, our results, I will not get to any technical details here, but we can discuss later if you want. So first, the three operations that we will use. First, the one that comes with measurement simulability. So I have two set of measurements, and the set tilde I is I simulable if I can simulate this or obtain the statistics of this measurement by pre and post processing the measurements on the set I. And what we get is that by doing this, we get a free operation that preserves the set of non-contextual behaviors in the scenarios where I change from the set of measurements I to the set of measurements I tilde. So what we get is that measurement simulability gives us a set of equivalence between measurements to be simulated and the measurements performing the simulation, and this gives me a set of free operations for these two different contextuality scenarios. And we also use a binary operation that is just the juxtaposition of the behaviors that I had before, much in the spirit of what was done by Abramsky, Samson, Hui, and Shane in previous work. I should have put it here. I will correct that before sending this to you. And this is also, as expected, a free operation for contextuality in this scenario. So with this, we get tools to derive sufficient conditions for contextuality. So the idea is the following. I have a complex scenario here and apply a free operation. I get a simpler scenario here, for example, the simplest scenario, but not necessarily just this, this is just an example. And the idea here is that if I start with a contextual behavior, if I start with a non-contextual behavior, I will end up with a non-contextual behavior here. So if after applying this free operation, I have something that is contextual, I had to necessarily begin with a contextual behavior over here. So the contextuality of the image of this behavior under this free operation is a sufficient condition for contextuality here. And again, we go back to that discussion. Why would I need such a thing? First, because it's not always possible to find or to characterize completely this set of non-contextual behaviors, because despite being linear programming, the number of parameters you have in this linear program grows exponentially. So maybe having sufficient conditions is good enough. And another reason is that sometimes this sufficient condition is what you need, exactly what you need in a specific application of this notion of contextuality. And this is what happens here, as I will tell you in a minute. And also the product, if I have two scenarios and I have the characterization of classical, quantum, and general sets of behaviors, if I have the product here, I'll have here some sufficient conditions for this characterization in the larger scenario, that is the product of the smaller scenarios. So again, this will not be necessary conditions, but they will be sufficient conditions, and this helps us to understand some scenarios, some complex scenarios in terms of simpler ones. Okay, so just a summary of our results. First, we find a way of witnessing quantum contextuality for that class of behaviors that I defined previously, using these free operations, and then using that product that I mentioned before, we prove that for scenarios of this type, we find quantum contextual behaviors violating non-trivial, every type non-trivial non-contextuality inequality. And this will be very useful for this, for when we study quantum advantages. So in general, we can think of these quantum advantages as the following. Imagine that we have a task that has a success rate defined by a given function g. And imagine that this function g can, or the bound for this success rate g for non-contextual behaviors can be expressed as a linear or as a function of non-contextuality inequalities. Then we show that there exists a behavior, a quantum behavior, that outperforms non-contextual behaviors for these specific tasks. So one of the scenarios, one of the cases that we looked at is the quantum cloning, state-dependent quantum cloning task studied in this paper here. And we see that this scenario that is used in this paper for proving that contextuality provides advantage for state-dependent cloning is related to this product of this simpler scenario, where this B6 is the scenario that was defined in the beginning of the talk. So we see that the contextuality that allows for advantage here can be witnessed, that can be seen as contextuality in this smaller scenario. So this provides a simpler way of talking about contextuality in these scenarios here. Okay, so this is what we have so far, but what would we like to do? First, find other applications of contextuality or other scenarios that we can understand using the same tools. And of course, use this to find other practical tasks that in which the quantum advantage can be connected to this notion of contextuality. So this is what we would like to do now, to use this to study other applications besides this state-dependent cloning. Okay, of course, we expect this to be also to also hold for other notions of non-classicality. So maybe we can also use these same tools. The mathematical tools are more or less the same to understand quantum advantages in other applications that rely on other notions of non-classicality. Okay, so that is what I had to tell you today. I would like to thank all people in my group. And now our meetings are like this, unfortunately, but as I said before, I'm happy that we still can get our work done despite the conditions that we are living here. And I thank you for the attention.
Hi, Barbara. I just wanted to ask you, you were mentioning that there could be other forms of non-classicality to which the same kind of analysis could be applied. Could you say a word about, what you had in mind for that?
Well, I have no specific practical task in mind, but what I have in mind is the following. This notion of finding sufficient conditions that using research theories, there is not specific for this research theory of this particular type of contextuality. So you can use the same tools to do the same in every research theory that you have, basically. So the thing is that maybe, of course, this is not maybe, this is for sure, you can use these the same techniques to find sufficient conditions for contextuality in, for example, the shift theoretic approach. And if you connect.
So would it be, so I mean, if just to, so are you saying for different definitions of contextuality or for things that are fundamentally different manifestations of non-classicality?
Yes, but the mathematical tools that we are using here, that is, of course, you are going to change what you call or what you call an object. You will change what are the free operations, but in the end, the same. Let me just show you the figure here. I think it will be clearer. In this picture here, what we are doing is the following. We have a complex scenario. We apply a free operation to get to a smaller scenario, easier to characterize. And then we use contextuality here to say something about contextuality here. So there's nothing special in this approach of this type of contextuality. We could use shift theoretic contextuality or any other notion. And now what we do is to use this tool here to understand what are the quantum features that allow for quantum advantage in this specific test of cloning. But maybe the same thing could be applied to an application of other forms of contextuality. So that's simply the idea, that this idea could be applied to other notions of non-classicality as well, connecting these to different applications for a specific application of this definition of contextuality.
Okay, yeah, thanks. Okay.